Welcome to the Master Electrician Prep YouTube channel, your go-to source for mastering the code, sharpening your skills, and passing the exam with confidence. Whether you're driving to the job site or studying late at night, we're here to break down the NEC, tackle real exam questions, and give you the tips and strategies you need to become a licensed master electrician. Let's get wired in and power up your future. The journey starts now. Today, we're taking a deep dive into a cornerstone of electrical safety: grounding, bonding, and neutrals from your Master Electrician's exam preparation materials. Our mission: to cut through the complexity, distill the most critical information, and ensure you're not just ready to ace the exam, but truly prepared for real-world scenarios.
Yeah, exactly. If we connect this to the bigger picture, mastering grounding, bonding, and neutrals isn't just about ticking boxes in the National Electrical Code. It's the absolute foundation for building safe, reliable electrical systems. That's where the science of electricity meets the practical art of ensuring every installation protects lives and property. Without a deep grasp here, the entire system is vulnerable.
That's a powerful way to put it. You really underscore how foundational these concepts are for safety. Let's start with that very first line of defense: grounding. What truly defines it, and why is it so critical as that initial safety layer?
Okay. Grounding is essentially our electrical system's ultimate shock absorber and voltage regulator. At its core, it's about establishing a solid connection of all non-current carrying metal parts of an electrical system to the earth. Think of its dual purpose. First, it limits dangerous surge voltages that could be imposed by external events like a lightning strike or a power line surge. And second, crucially, it stabilizes the voltage during normal operation, preventing dangerous fluctuations that could damage equipment or, more importantly, injure someone.
So it's not just about throwing a wire in the dirt then. The NEC, especially Article 100, is incredibly precise with its definitions, which I know can sometimes trip people up on the exam. What are some of those key terms that an aspiring master electrician absolutely needs to clarify in their mind?
You're right, the precision matters. For both the exam and actual practice, grasping these distinctions is vital. Let's start with bonded. This simply means the connection of interconnected parts to form a continuous conductive path. Then we have bonding conductor or jumpers, which are the specific wires used to make that connection.
Okay, so if I'm tracking, bonded is the state of being connected, and bonding conductors or jumpers are the actual wires that make that connection happen. That nuance is critical. What about the actual earth connection?
Exactly. And that's where the grounding electrode comes in. This is the conductive object, like a ground rod or even a metal underground water pipe, that establishes the physical electrical connection to the earth. From there, a system or circuit is considered grounded when it's connected to earth, or to a conductive body that extends to the earth.
And the conductor itself, that's specifically grounded.
That's the grounded conductor, a specific system or circuit conductor that is intentionally grounded. This distinguishes it from, say, an equipment grounding conductor. And critical for safety, we need an effective ground fault current path. This is the intentionally constructed low impedance pathway designed to carry ground fault current back to its source, which is what we need to make sure the overcurrent protective device, like a breaker, trips quickly.
Got it. Makes sense.
Lastly, a ground fault itself is simply any unintentional electrical connection.
That's a fantastic breakdown. And if you're looking at your materials, Figure 5.1 really paints a clear picture of how all these elements, from the service equipment to the literal earth connection via components like a ground rod or building steel, work together in a grounded system. It's like seeing a blueprint for electrical safety in action. So we've defined grounded. Now, what about the grounded conductor itself? It's often the neutral wire in our systems, but how does it specifically differ from the broader concept of grounding, and why is it so important?
That's a great distinction. A grounded conductor is a circuit conductor that's intentionally grounded for operational purposes. In most electrical distribution systems we deal with, this is indeed the neutral conductor. The NEC, particularly Section 250.24, is very clear that a grounded conductor must be supplied for services. If you're looking at your materials, Figure 5.2 visually breaks down its role in calming systems like three-phase, four-wire WIE, and three-wire corner-grounded delta configurations. It's the path for return current under normal conditions.
Right, the return path. And when it comes to sizing this grounded conductor, that's a critical aspect for compliance, right? It's not a one-size-fits-all scenario, and getting it wrong can have real consequences.
Precisely. The sizing rules are quite specific because it carries current. The grounded conductor shall never be smaller than 12.5% of the largest service entrance phase conductor. You can visualize this with Figure 5.3 in your materials. For instance, in an application question, If you have a service with a 225 ampere circuit breaker and 250 kilosamo copper ungrounded conductors, the required grounded conductor size is 2 AWG copper. It's about ensuring it can safely carry the potential unbalanced current without overheating.
Okay.
If you have conductors installed in separate conduits, Figure 5.4 demonstrates that you base the size on the total circular mill area of the phase conductors. Always refer to your tables for specific values.
So we've covered how we ground the system for safety and how the grounded conductor manages operational current. But bonding. Bonding often gets mentioned alongside grounding, and it has a distinct and equally vital role. Let's dig into the crucial main bonding jumper first.
Right. Think of the main bonding jumper, or MBJ, as the emergency express lane for fault current. It's the conductor that electrically connects the system grounded conductor to the equipment grounding conductor or the supply side bonding jumper. Its primary purpose is to provide an effective ground fault current path, ensuring that when a fault happens, that current immediately rushes back to its source, creating a surge large enough to trip the breaker. Without this dedicated low-resistance path, that current might wander through anything conductive, a person, a metal conduit, rather than safely shutting down the system.
So it's about forcing the fault to clear rather than allowing it to linger dangerously. How is the MBJ typically installed and where?
Exactly. It could be attached with a green screw, exothermic welds, or listed pressure connectors. Crucially, the MBJ is only installed at the service. Disconnecting means never downstream or in subpanel.
It's only at the service. Okay.
This is key for exam purposes. Sizing follows NEC 250.28D and cable 250.102 Ray. It's never smaller than 12.5% of the largest service entrance phase conductors. For instance, if you have a 750 kilomole copper service, your main bonding jumper would be 30 AWG aluminum. Figure 5.5 clearly illustrates this.
That makes perfect sense for ensuring a clear fault path right at the service. But what about other types of bonding jumpers we might encounter in the field?
Good question. Beyond the MBJ, we have general bonding jumpers, which simply connect two or more metal parts to ensure electrical continuity. These must be made of copper or corrosion-resistant materials and can be installed inside or outside a raceway or enclosure with a maximum 6-foot length permitted outside, as shown in Figure 5.9.
6 feet max outside. Got it.
Then there are supply-side bonding jumpers used on the supply side of the service. Their sizing is similar to the MBJ, also following the 12.5% rule in NEC 250.102C1, which you can see in Figure 5.10. For equipment bonding jumpers load side, which are used in feeders or branch circuits, their role is to connect equipment grounding conductors on the load side of the service. Their sizing is determined by NEC 250.102 and Table 250.122. For example, a 400A feeder would require a 3 AWG copper equipment grounding conductor, as depicted in Figure 5.11. Finally, system bonding jumpers establish the connection to the system grounded conductor for separately derived systems, like transformers. Their sizing uses NEC 250.28A and Table 250.1021, applying that same 12.5% rule for larger services. Figures 5.12 and 5.13 show their connection points with transformers and disconnects.
So we've covered the critical continuity bonding creates and the importance of the grounded conductor, but how does all of that ultimately connect to the Earth itself? That's where our grounding electrodes and their conductors come into play, right? This is where the code gets very specific about what's permitted for grounding electrode conductors and grounding electrodes.
Exactly. The grounding electrode conductor, or GEC, is the final physical link. It's the conductor connecting the system grounded conductor or the equipment to a grounding electrode, or a point on the grounding electrode system. It can be copper, copper-clad aluminum, or aluminum. Sizing is governed by NEC 250.66 and Table 250.66 in your materials, with a minimum of 8 AWG copper. But it's not necessarily larger than 4 AWG copper when multiple electrodes are used. This conductor is what connects your entire system to things like ground rods, metal underground water pipes, and plate electrodes.
Okay.
A specific detail crucial for the exam is that a concrete encased electrode must use a 4 AWG or larger copper conductor.
4 AWG for concrete encased. And what about the actual physical grounding options? The NEC doesn't just let us use any old piece of metal, does it? What are the primary methods outlined in the code?
No, absolutely not. No. Figure 5.6 lays out the 4 primary grounding options, each with specific requirements. First, a middle underground water pipe, which requires a minimum of 10 feet of direct contact with the earth.
10 feet minimum.
Second, the metal frame of the building can serve as an electrode, provided it meets specific criteria. Third, a concrete encased electrode, often called a UFER ground, which needs a minimum 20-foot length of 4 AWG or a larger conductor, encased in at least 2.5 inches of concrete at the bottom. And fourth, a ground ring, which requires a minimum 20-foot length of 2 AWG copper conductor buried at least 2.5 feet deep below the Earth's surface. Each method has its specific use case and installation requirements that master electricians must know.
Okay, so we've connected to the Earth. Now, how does the equipment itself get grounded to ensure safety? That's where the equipment grounding conductor, or EGC, comes in. It's often green for a reason, right?
It's green for a very good reason. The equipment grounding conductor, or EGC, provides that final, essential, low-impedance path between electrical equipment and enclosures and the system-grounded conductor, or grounding electrode conductor. Its purpose is vital. If a hot wire accidentally touches a metal enclosure, the EGC ensures the overcurrent protective device, OCPD, operates quickly, clearing the fault and preventing that enclosure from becoming energized and dangerous.
So the EGC isn't for carrying normal operational current, it's purely for safety. To clear faults immediately, what forms can it take?
Precisely. It's a dedicated safety net. EGCs can be bare, covered, insulated, which is often green, or even integrated into metallic conduits, as permitted by NEC Article 250.118. Sizing is critical and determined by NEC 250.122 and Table 250.122 based on the OCPD size or appliance rating. For instance, a 30A OCPD requires a 10 AWG copper or 8 AWG aluminum EGC. You'll find these examples and more in figures 5.7 and 5.8 in your materials, which also show how they work for multiple circuits in a common raceway.
Okay. Now, neutral conductors are a bit different from grounding wires, but just as important, especially when we talk about unbalanced loads. This is where mastering calculations becomes key for your exam.
You're right, the math gets interesting here. The neutral conductor is a grounded conductor connected to the neutral point of a system. Its primary functions are carrying the maximum unbalanced current and contributing to the effective ground fault current path. NEC 250.24C 1 and 2 dictate its sizing to ensure it can safely handle that maximum anticipated unbalanced current, which is essentially the difference between the ungrounded phase currents. Figure 5.15 in your materials shows the neutral connected to its supplying transformer.
So unbalanced current for single-phase systems, that sounds relatively straightforward, but for three-phase Y systems, it gets a bit more involved, doesn't it?
For single-phase neutrals, calculating unbalanced current is straightforward. It's the absolute difference between the phase currents. So if you have 30A on phase A and 20A on phase B, your unbalanced current is 10A, as shown in figure 5.16.
Okay, simple difference.
Now, three-phase Y neutrals are indeed more complex because the phase currents are 120 degrees out of phase. The unbalanced current formula involves the square root of A plus B plus CP clo ADB plus BC plus TA. For example, with 50A, 30A, and 65A at 208V, your unbalanced current calculates to 30A.
Right.
Figure 517 also briefly touches on a high lag in three-phase delta systems, that's typically phase B, measuring significantly higher voltage to ground than the other phases. A critical distinction for safety in wiring.
Mm-hmm. Important to identify that high lag.
Absolutely.
Yeah.
And figure 518 shows common three-phase Y service voltages you'll encounter.
And speaking of calculations, sometimes you can actually derate neutral conductors, which sounds like it could simplify things, but has specific rules, right? This seems like a prime area for exam questions that test your precision.
It certainly is. NEC 220.61B2 and C allow for deturating the neutral conductor's demand factor to 70% if the unbalanced load exceeds 200A. It can save on material costs, but there are crucial exceptions you must know for the exam. You cannot deturate for nonlinear loads like computers, printers, or other electronic equipment operating from a 4-wire Y system.
Why is that?
Well, this is because these devices create harmonic currents that can significantly increase the neutral current, sometimes even exceeding the phase currents, even with balanced phase loads. So no deuterating there.
The harmonics issue. Okay.
Also, no deuterating is allowed if the load is supplied from a 3-wire circuit using 2 phases and a neutral.
Got it. Those are critical exceptions.
Let's run through a couple of quick examples from the source material to illustrate the calculations. If you have a 400A total unbalanced current with no nonlinear loads, the first 200A is rated at 100%, and the remaining 200A is then rated at 70%, which is 140A. This results in a total demand of 340A for your neutral.
Okay, 340A.
Now, if you have a 690A unbalanced current that includes 250A of nonlinear current, the calculation changes. The first 200A is at 100%. The 250A nonlinear current is also at 100% because of those harmonics. And only the remaining 240A is rated at 70%, which is 168A. This brings your total demand to 618A. It highlights the absolute precision the NEC demands.
Wow, yeah, that really shows how much impact nonlinear loads can have. You really need to know those rules. Finally, let's explore a couple of specialized grounding systems that master electricians might encounter, designed for unique operational or safety requirements that go beyond the standard setups.
Right. First, ungrounded systems. These are defined as systems that do not have a grounding electrode at the supply transformer. Their unique behavior is critical to understand. If a first ground fault occurs, current flows to earth, but the system often continues to operate without immediate tripping. It's not until a second ground fault occurs on a different phase that overcurrent devices typically clear the fault.
So the first fault doesn't trip the breaker.
Often, no. Because of this, NEC 250.2 Week 1 emphasizes the necessity of ground fault detection systems for ungrounded systems to provide crucial warnings, allowing personnel to address the first fault before it becomes a major problem.
Detection is key there. Okay,
Yeah.
what's the second type?
Second, we have high-resistance ground systems, or HRGSs. These are used as an alternative to ungrounded systems in situations where an orderly shutdown rather than an immediate trip upon a ground fault is critical. Think of continuous manufacturing processes or critical IT infrastructure.
So avoiding sudden shutdowns, how do they work?
How they work is quite clever. A resistor limits the ground fault current to a very low range, typically between 3A and 7A, while fault detectors provide signals. The setup prevents the immediate operation of overcurrent devices, giving personnel time to identify and address the fault before a complete shutdown. You can see this illustrated in Figure 519.
Interesting. So it allows controlled response rather than immediate cutoff. So what does this all mean for you as you prepare for your master electrician exam? It means mastering these concepts isn't just about passing a test. It's about building safe, compliant, and reliable electrical systems that protect lives and property. Grounding, bonding, and neutrals are absolutely foundational.
And this raises an important question. When you consider the immense detail and specific measurements involved in grounding and bonding, from the minimum length of a concrete encased electrode to the exact calculation for degrading an unbalanced neutral, what real-world scenario most powerfully illustrates the consequence of not adhering to these precise code requirements?
Yeah.
How might a single overlooked detail impact system integrity or safety, perhaps leading to a dangerous shock, equipment damage, or even a fire? Thinking about that level of precision truly highlights the meticulous nature of mastering the NEC.
A fantastic thought to wire into your mind. Thank you for joining us on this deep dive into the National Electrical Code. Keep studying, keep applying these principles, and remember, your journey to becoming a licensed master electrician is now wired in and powered up.